Hi guys. So today let's talk about martingales. And martingales are extremely important in finance because they are the foundations for no arbitrage theory and risk neutral pricing. Okay? So in this class what I want to do is I want to describe what a martingale is, and later we're going to use this martingale property when we're doing risk neutral valuation. So let's start with the adaptive stochastic process. And by adaptive stochastic process, I mean we have a sequence of random variables m0, m1, m2, mn, where each one of the random variables mn depends only on the first n coin tosses. Okay, this is called the adaptive stochastic process. Now we say adaptive stochastic process is a martingale if we take expectation at any time n of a random variable mn plus 1, then this is equal to m of n for all n from 0 to n minus 1. Okay, so as you can see, this basically is a one step ahead property. So we basically are taking expectation at time n of a random variable m of n plus 1. Okay, now we can also make it a two-step property. So m of n plus 1 we can write as expected value of n plus 1 m of n plus 2, right? And this comes from our martingale property, right? So if you can write it like this, and you can see we can take iterated conditioning here, and that would make it m of n plus 2 equals mn. Now this has become a two-step ahead property, right? Now the random variable is two steps forward. Now likewise we can actually do it for mn plus 3 likewise, and we can make a generic expectation. What we could say is expectation at time n of a random variable m is equal to, so this is called a multi-step ahead martingale property. Okay, so it follows from here that m0 is equal to expectation at time 0, so I don't have to write a subscript here, of m1. Okay, and from a multi-step ahead property I can also write expectation of m2, expectation of m3, expectation of mn. So as we can see from here, for a martingale process the expectation remains constant, okay, as we go forward. So the expectation doesn't change. Now what I would like to do is let's actually apply this property to our simple model. Okay, we basically had defined a stock process where at time 0 the stock was at 4. If we tossed the head, then the stock went up to 8. If we tossed the tail, then the stock went down to 2. Okay, now let's define a probability measure under which probability of getting a head is 1 by 3 and probability of getting a tail is 2 by 3. Let's calculate. What I would like to calculate is expected value at time 0 of random variable s1. Okay, and what would that be? At time 1, random variable can be either 8 or 2, right? With probability 1 by 3 and 2 by 3. So expectation is 8 times 1 by 3 plus 2 times 2 by 3 equals 12 by 3 equals 4, right? And 4 is the same as where we started. So this can be written as S0. So from here we can see the expected value of random variable S1 at time 0 is equal to S0. And this pretty much is the same thing as how we define a martingale, right? So we said for a martingale, expected value at time n of mn plus 1 equals to mn. So likewise here. Okay, so this basically becomes the martingale under this probability measure. But if we had defined the probabilities to be probability of a head to be half and probability of a tail also to be half, then the expected value would have become 8 times 1 by 2 plus 2 times 1 by 2 equals 5, right? Then the expectation would not have been equal to S0. So in this case, in this probability measure, we can see S0 is less than expectation at time 1. And such processes are called sub-martingale. Okay? So martingale, the expectation is 0. Sub-martingale basically have a tendency to rise. So we can see expectation of S1 at time 0 is higher than S0. So they tend to rise. Okay? If on the other hand, in another probability measure, if it was like this, if the expectation had a tendency to go down, then this would be called a super martingale. Okay? Sub-martingale, super martingale. Sub-martingale have a tendency to rise. Super martingale have a tendency to fall. But martingale, basically the expectation remains constant. Okay? The expectation doesn't change. And this is actually extremely important. Martingales are extremely important in mathematical finance, as we will see later. So at this point in time, that basically what I wanted to talk about in this particular lecture. So we've defined what a martingale is, and I showed you, under this measure our stock process was a martingale, and this measure our stock process was a sub-martingale. Okay. So in the next lecture now we're going to try to come up with our risk neutral pricing formula for a binomial asset pricing model. Okay, and there you will again see martingales, and hopefully the concept is going to get clearer. Okay, all right guys, thanks.